Hi guys. In this video we will look to finish up stereochemistry by looking at a few remaining topics in the handout. We'll begin here with this homework question, which hopefully you have attempted. How many chirocarbons does the following glaucoma drug contain? Chirocarbons. I see one here. That carbon is attached to 4 different groups with an undrawn H. I see one here. Tetrahedral carbon with 4 different groups. Same there. Same there. Same there. And it looks like that is it. This carbon here is not chiral. It has 2 methyl groups attached. This isopropyl group on the oxygen, an isopropyl ester. How many chirocarbons? I see 5. How many sterogenic centers does it contain? Well, at least 5, because a chirocarbon is a sterogenic center. But we also have sterogenic alkenes. This alkene, sterogenic, it's shown as cis. It can be trans. That is, there's 2 options for this alkene. Just like there's 2 options for the configuration at each chirocarbon, we call those 2 options R or S. This alkene is also sterogenic. It's currently trans, but it could be shown as cis. Carbon-carbon double bonds here, alkenes. The so-called alkenes in the benzene ring, they're really not alkenes, but they are carbon-carbon pi bonds. They're not sterogenic. They have to be, the 2 bonds in the ring have to be cis to each other in order to make a 6-membered ring. Only with larger size rings can the 2 bonds about a double bond like this be trans in a ring. Now the carbon-oxygen bond, of course, is not stereogenic. There's no stereochemistry there. Only the carbon-carbon double bond, the alkenes, are stereogenic. There actually could be other double bonds that are stereogenic, but nothing that we have seen, and certainly not a carbonyl. There's no stereochemistry about a carbonyl possible. Okay, how many stereogenic centers does it contain? It looks like it's 5 plus 2, 7. How many total stereoisomers possible? 2 to the 7 equals, what is that? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Yeah, we need to keep going, right? Yeah, clear. 2 times 2 times 2 times 2 times 2 times 2 times 2. What is that, 128? Yeah. I have a new calculator here. I need to make sure I know how to work it, right? You don't want to get caught on a quiz not being able to work your calculator. Actually, I don't see an exponent on my calculator. Well, I'm not going to keep looking. I think it's 128. 2 times 2 times 2, 7 times. Okay, there we go. Definition of diastereomers. We've actually mentioned that several times already. It's in the In our diagram here, stereoisomers that are not mirror images, such as cis-trans, erythro or threo, diastereomers. Okay. I mean, if you have an alkene, like simple alkene, like 1,2-dichloroethene, if this looked in the mirror, this is cis, okay? I just turned it to the side there, cis. If this looked in the mirror, well, it would also be cis. The mirror image of cis is cis. If this thing looked in the mirror and it looked like this instead, okay, those are not mirror images. This is trans. The mirror image of cis is not trans. Okay, the mirror image of cis is cis. Cis and trans are thus, they are stereoisomers. They're both 1,2-dichloroethene, or ethylene is the slang name. Both of these are 1,2-dichloroethylene, but one is cis, one's trans. They're stereoisomers that are not mirror images. Stereoisomers that are not mirror images are diastereomers. Okay? Also erythro or threo. Things that are mirror images are RNS or DNL. DNL represents a DL pair. Of course, enantiomers. Enantiomers are mirror images that are different. Okay? Now, all these are different compounds. All right? Different compounds. Before any of this applies, you need to make sure that you're not looking at same compounds. For example, right here, these two are mirror images, yes, but they're the same compound. So you would not call these two enantiomers. You would call them identical. Okay, so we've already looked at diastereomers, but let's look at epimers. Epimers are also diastereomers, okay? There's diastereomers. It's a subclass of diastereomers. Of course, diastereomers are indeed stereoisomers, but epimers are diastereomers that differ by only having one center reversed. When multiple stereocenters are present. And this usually refers to a chiral carbon. I could say chiral center, but I'll go ahead and be more specific with a chiral carbon. That's the most common. Okay? And epimers are seen with carbohydrates particularly. And that's where we can look to understand what an epimer is. This page here. If you look at these two carbohydrates here, ribose and arabinose, they are epimers because first off, these are Fischer projections, and if you just switch the sides of your Fischer projections, you are switching between R and S. Okay, so if you look at this second carbon here, this is C2. Okay, the carbonyl is C1, C2. If we look at these two molecules, the only thing that's been switched here is one stereocenter, and it's C2. The other two stereocenters at C3 and 4 are identical. They have not been switched. And so these are epimers because we've only switched one stereocenter. Now, we can clarify where that switch took place by stating something like C2. And we understand that ribose and arabinose just have a different configuration at C2. On the other hand, if you look at idose and talose, these are C3 epimers. Now these are 6 carbon sugars, and these have 4 chiral carbons total. But the only difference is where? Well, C3, right here. The only difference is the configuration at that carbon has been switched in going from this molecule to this one. The other 3 stereochemical sites, or we could say sterogenic sites, chiral carbons, are the same. So only one of the stereochemical sites or stereocenters has been changed. And we call these C3 epimers. I gave you some other examples here. We could say that D-mannose is the C2 epimer of D-glucose. Okay, here's D-glucose, here's D-mannose. What's the difference in the two? I'm sorry, that's not glucose, that's gulose. Here's glucose. I was looking at it as like more than one change here. I mean, if we look at these two, well, there's 3 changes. C2, 3, and 4 are different when you come over here. So those are not epimers, because more than one thing has changed. More than one stereocenter has changed. But if you look at mannose and glucose, there's only one change, and it's at C2. And so these two are C2 epimers. Now back over here, since I started by pointing these out, these two are, what is the relationship between those two? Well, first off, they are stereoisomers because they all have the same connectivity. C2 has an OH and an H, C2 has an OH and an H. C4 has an H and an OH. C4 has, they all have the same groups attached at the same carbons. But the groups are projected differently. These are stereoisomers, okay? Well, all of these are stereoisomers each other. We can get more specific than that. There's 2 types of stereoisomers. Are these mirror images? Well, no. None of these are mirror images. The mirror image of this would look like those 3 carbons are actually mirroring, but the 4th carbon is not. We need to switch the OH here and here. Then they would be mirroring. They're not stereoisomers, so they must be diastereomers. And indeed they are. Stereoisomers that are not mirror images. Well, are they epimers? Epimer is a type of diastereomer. Well, no, they're not. They're not epimers. Because more than one stereocenter has been changed. All right. Now I gave a question here. What is the enantiomer of a compound that has 4 chiral carbons with a configuration of RRSR? Well, the enantiomer would be where everything is switched, and the enantiomer would be SSRS. Well, what would be a diastereomer? Well, there's many possible. Many. RSSS would be one, because this is a stereoisomer, but it's not a mirror image, so it's a diastereomer by default. What would be an epimer? Well, epimer is where you only change one stereocenter. And there could be 4 different epimers, because we could change 4 different stereocenters One of those four would be where we just changed the last one, and instead of having RRSR, we could have a molecule that is RRSS. Okay? Now, of course, this would also be considered a diastereomer, because epimers are always diastereomers. All epimers are diastereomers, but not all diastereomers are epimers. Miso compounds, we've already covered that. You can read some there. I think we've covered that in the previous video. Okay. What I'd like to do now is this problem here, to bring in some of the stereochemistry in our alkene reactions, and to sort of really look at this and sort of finish up this discussion here. So show the product of the following reaction in a Fischer projection with the isopropyl groups at the top and bottom. Well, let's do that first, and then let's move on and answer some questions. Okay, we have an alkene, ICl. We know we have a dipole here. This is partial plus, partial minus. The iodine is electrophilic, that is, electrons are attracted towards it. Or we can say it likes electrons to be attracted towards it. These electrons attack. I'm going to go through just abbreviated mechanism here, not a full-fledged mechanism as like a test question, but just the thought process. Attack the iodine, going to leave carbocation on the left. If I don't do any stereochemistry, the product will be iodine here and chlorine on this carbon. I'm going to draw it, however, just wherever I have room to draw it. Okay? Alkene attacks iodine, it back bonds, and then the chloride comes in and attacks where would carbocation form. That's where the chloride would attack, kicks the iodine back off. Get this product here. But what is the stereochemistry here? This is where, if we remember in class, I suggested that you turn this first, and let's make it projections. Let's put the isopropyl back, and let's put the methyl back, and let's put this isopropyl, I'm sorry, those are actually forward. Let's put this isopropyl back. Now let's put the two groups on. But what do we know about the addition of these two groups? Okay? Anti-addition. Alright? Now I'm not going to review anti-addition every time I mention anti-addition. At this point, I would hopefully you know that, okay, this is just like reaction with ClCl. The only difference is you've got a different halogen, so we need to consider regiochemistry. So anti-addition, and what we can do is get rid of one of the double bonds. Now I'm using pen. Get rid of one of them. We can put the chlorine here straight up and put the iodine here straight down. Now if I can go ahead and draw in the undrawn H. That way on each chiral carbon, which they're now both chiral, we see a complete tetrahedral, one forward, one back, one forward, one back. There we go. But this is also going to be plus enantiomer. And the enantiomer would look, I'll do it over here. Pretend there's a double bond there. Let's go back to the original that I had here. And instead of putting the chlorine up and the iodine down, put the chlorine down and the iodine up. Now I will go back over here. This is going to form an Iodonium Ion. Okay. A double bond has a top face or bottom face. This attacks here. Okay. Let me show it concertedly. That gets kicked off. These electrons come right back over here, but this is all from the bottom. All right. From the bottom. But this can also take place from the top. This attacks here, that kicks off. The iodine comes right back down. Again, I'm not showing an NAF intermediate here. And that would give the iodine up. Okay. There you go. You're going to get both. All right. These are actually enantiomers. They're not drawn as mirrored. But if you turn this one way and the other one the other way, you would then see that they are mirroring each other, and they're different. Those are enantiomers. But that's what I drew here. Well, I haven't got it yet. How do we get this one? Well, this one comes from the chloride. Okay, the iodine is straight down, the leaving group is straight down, so this comes in straight up. And this leads to this product. The iodine is straight down when it gets kicked off, but the chlorine is straight up. The dash and the bold stay the same. Over here, the chloride, the iodine is up, and so this comes in from the bottom, kicks that off, and so the chlorine would be down and the iodine would be up, and that's what you get here. So you get this plus the enantiomer. Okay. You can draw them both, but it's very common to just show one and then say plus enantiomer. We need to show the product of a Fisher projection with isopropyl groups at top and bottom. All right, let's stand on the ground over here. Either side will have an isopropyl group at the bottom and one at the top. If I'm over here, let me stand here and look through here. And with the chlorine going away, I have two chiral carbons adjacent to each other. So I have a crosshair with two chiral carbons adjacent to each other. And with the chlorine going away, this is a methyl, I'll clarify that. The methyl is on my right and the isopropyl is on the left. With the iodine going away, now let's keep our feet on the ground. At some point, you will have your feet in the air. Okay? Feet on the ground. With the iodine going away, the isopropyl is coming off the page this way. If I'm over here, this way is to my left. With the iodine going away, isopropyl is on the left. Both of them are like that. The undrawn H by default must be on the other side. So here's the perspective drawing drawn as a Fisher, but the directions told us to put the isopropyl groups at top and bottom. Well, we can just now rotate this way and this way. And if we rotate, we will get isopropyl at top. That's not a chiral carbon. We don't need a crosshair. Chlorine moves here. Methyl moves here. Bottom carbon, isopropyl at the bottom. Iodine moves here. And H moves here. And here's the product in a Fisher projection with isopropyl groups at top and bottom. Now you actually could have made the ground over here, because if you made the ground over here, that isopropyl group would have been closer to the ground. And that would have also fit the directions. Now if you do Fisher of this, you will end up with, you can do it, but guess what it will look like? It'll look like that. We already said that's the enantiomer of this. If you look at your two Fishers, you see how they're mirroring each other? Yes. Prove it to yourself. But again, it's okay to just show one and then say plus enantiomer. It didn't say draw both. Is the product chiral? Well, it has two chiral carbons. But that doesn't necessarily mean it's chiral as a whole, because there could be an internal plane of symmetry, and that would be called a Miso compound. I don't see a plane of symmetry. If we cut through here, you'll have a chlorine on one side and an iodine on the other, a methyl on one side, a H on the other. If you cut through here, you'll have a methyl on one side, chlorine on the other. There's no plane of symmetry. The mirror image is different. Is the product chiral? Yes. If so, also show the enantiomer in a Fisher projection. Oh, we already did that. Okay, we were asked to do that. That's the enantiomer. When drawn as directed, is your product erythro or threo? Well, the high priority groups are on the same side in the Fisher projection, so that would be erythro. Now the enantiomer is also erythro. Both erythro. I really don't need to clarify that. The mirror image of erythro is erythro. Let me draw another stereoisomer here. What if I drew methyl chlorine isopropyl like this, but just put the iodine here and the H here? Okay? Are these two mirroring each other? No, they're not. Well, first off, is this erythro or thrio? Iodine and chlorine, this is thrio. An erythro compound and a thrio compound are not mirror images. They are stereoisomers. So what type of stereoisomers are they? They are diastereomers. Erythro and thrio are diastereomers. Now these two could also be called epimers, because in going from one to the other we only changed one chiral carbon. Again, if you just switch positions on the sides in your Fisher projection, you are going from R to S if the carbon is chiral. Is this reaction regioselective? Yes. That's because the chlorine is only going to bond to the tertiary carbon. We do not expect a regioisomer with the chlorine bonded here and the iodine bonded there. There's regiochemistry built into this reaction, yes. Is it stereoselective? Is the reaction stereoselective? That's a general term. Let's get more specific. Is this reaction enantioselective? No. Both enantiomers formed. Right? These are the two enantiomers. Why are they both formed? Well, mechanistically. And I'll give you a little free information. None of the reactions we've done so far in this class are enantioselective. Next, is this reaction diastereoselective? The answer is yes. Only erythro formed, not thrio. This reaction did not give a diastereomer of these. The diastereomer would be 3O. It was not formed in this reaction. So we do have selectivity for diastereomers, that is, erythro was formed, not 3O, but we don't have selectivity for enantiomers, because both enantiomers were formed for our product. Stereoselective is too general of a term because that could include a look at enantiomers or diastereomers. So if you're ever asked this question here, I would ask you to ask for clarification. Okay, so this is sort of the full discussion of alkene chemistry and then fully addressing the stereochemistry in our product. And we're able to review a number of different things here, particularly drawing Fisher projections, rotating, using correct terminology like erythro or 3O, etc. Okay. You can read a little bit here about what we just talked about. G, resolution of enantiomers by conversion to diastereomeric salts. I'm not going to cover that here by video. We may look at that in class, but that's mentioned on the last page in the handout. Okay, please look at that. This will be relevant for the one of the worksheets, the polarimetry worksheet for the lab. Basically, how can we separate enantiomers? All right. That's rather difficult because they have same physical properties. But if we can convert the enantiomers to diastereomers, diastereomers have different physical properties, such as different polarity, different solubility, and much easier to separate diastereomers. Then after we separate them, if we can then convert back to the enantiomers, we can accomplish our goal. Okay, the last mini topic here is please note that capital DL is different from little dl. Okay, little dl is the rotation of pp light, either to the right or left. Okay, lowercase. Capital DL means something different. And we're actually not going to be looking at what capital DL means. You will likely do that in biochemistry. But I give you just a little information on that. So make sure that you understand that there is a difference. And always use little d, little l for the optical rotation designation. Okay, what else can we say here? Brief history of chirality. Hopefully that's sort of interesting, informative. Some of how the science developed over time. And we will sort of be focusing on this warm-up page, and we'll probably do some of this in class. Okay, particularly where's Waldo, identifying planes of symmetry here. Think about these. This will be some review of stereochemistry, and then there's some questions here which are very similar to what we just worked with the ICL reaction. And of course you also have your workbook and textbook for working problems. Okay guys, I just wanted to add a little bit additional information here. Okay, we're getting to the point where it's becoming a little bit miscellaneous, but hopefully this was useful as we finish up stereochemistry.